Let's see if I remembered how to hit the go live button. It's been a minute. It's been a minute. Cool. Let me make sure I'm live on YouTube. If you all see me looking around like an idiot, I'm just checking if my audio is going through. It's been a minute, everyone, since I've live streamed. Cool. I can hear myself. Hey, everyone. It's been a minute since I've live streamed. That's because I've been reading a lot of papers. You see that stack of papers there? Yeah, I started with reading papers physically and then I graduated to this. By the way, many people ask what this is. It's a remarkable too. They're not paying me. I wish they at least send me a free one. I'm being cheeky. But I've been reading papers on this and I've been doing a lot of LLM reading. So this will be the first of many large language model live streams where every hopefully Saturday or every weekend we'll go through different LLM papers. For all of you that have been waiting for the generative AI roadmap or the LLM roadmap, I've been working on it. It's going to take a few more days. Other things I've taken up, but it's coming soon. So please stay tuned for that. Things have been very purple, things have been very black. If you know, you know. But we're back on track and we're here to study. So thanks for joining. So this is the first of many reading groups. Hopefully, I've decided every weekend I'll pick my favorite paper from the week and we'll go through that together. If you're new to the study group, we usually hang out, discuss papers, and talk about them. And I try to give you a good gist of any paper that we're trying to go through. So for today, we're gonna read through this one. Textbooks are all you need, and if you all are interested, I've been tweeting about all of the papers I've been going through pretty much every day. So the tweets should give you a gist how these study groups are structured. Are I'll give you a gist in the first 5 minutes, and then you can decide if this discussion is worth your time or not. If it is, we'll go through the entirety of the paper and discuss it in every minute detail. And if you don't have the interest in the paper, you can go through it in the first 5 minutes, get an overview, and move on with your life. There are a lot of papers coming out pretty much every day, and I'm sure we all are very busy with everything. So this paper sort of looks at how to outperform larger models with better data, and the age-old saying "garbage in, garbage out," or can we improve scaling laws by improving our data quality? So the goal for this paper is to create models that are good at writing Python code, and they only have one mission, which is to write code based on doc strings. Very simple programs, nothing fancy. It's not like uh, what's the project that was trending recently? GitHub GPT. Um, there was a project trending recently, right, on GitHub, where you could like give a README and the project will write the entire file. I'm sorry, I can't remember the name, but if anyone in the chat can correct me. Yeah, so this is not trying to solve that. This paper only tackles one challenge of writing very simple Pythonic code based on doc strings, right? Sorry, I had a pop-up come up which I need to close. There we go. And this also means the benchmarks are just limited to that, but I still think it's an interesting read because it sort of challenges the scaling laws by showing that hey, a lot of these LLMs that everyone is working on are trained on a lot of garbage data sets, and if we can sort of clean those up and also come up with some other interesting things, we can really improve upon these models. So we first of all clean up the data set that all of these programmer helping models have been trained on. And after that, we also look at how to use GPT 3.5 to create a synthetic data set, which is added to the earlier one. And finally, I think this one is really cool. So please pay attention to this bit. We asked GPT 3.5 to create a set of exercises or questions on which we fine tune the model. And the cool part is this fine tuning stage sort of creates emergent abilities. So emergent abilities are where models start to show abilities that they have not been trained on. So let's say you train a model to say coffee is nice, and then it learns that it is not, and it starts telling everyone about chai. That is an emergent ability, and that's how all models should be. In this context, it means that the model has learned these exercises, but it is able to solve problems outside of it. It is able to understand APIs it's not been trained on and come up with very simple logic. So this is a 1.3 billion model that we're looking at, which means that it's not able to come up with very complex logic, but still it will be able to solve quite a few things. Cool. So that is the gist of the paper. If this still sounds interesting to you all, we'll now go in a further level of depth and we'll see what the authors have exactly done. But that is the simple gist. We take the data set that everyone has been working on and we sort of end up with a data set that's 100x smaller than most other models. We tune it on the deduplicated data set, then fine tune it on this careful synthetic data set that we've created, and we get a very nicely performing model that's much better than everything else. And also takes lesser data, is cheaper to train, is smaller in size. Perfect end result that we could hope of. But it's only on two simple evals, which only test one simple ability. So that is the catch here. I still think it's quite interesting because it's a small niche. Pick what you want. I'll say niche. Small small niche model that can solve just one task. And I think that's relevant in the context of creating customer support bots or similar chatbots. So that's why I thought this paper is worth covering. Anyways, I wanted to also tease out the LLM roadmap. So as you can see, I've been putting down my notes, sort of collecting all of the tutorials I've gone through. This will actually be a collection of all tutorials or all my course notes, all the courses I've taken, and all these interesting blog posts that I've read recently. So you can see I've just right now only put the name or the title of all of the blog posts. A few of the ones I've enjoyed, but eventually you'll have all of my notes in there. So this is what I've been working on if anyone is interested. And just consider subscribing if you're interested. So whenever this goes out, whenever I share the final LLM roadmap, I'll probably announce it on the channel. So that's the best way to stay updated with it. Cool. Let's get another level of a summary of the paper. So here are the first few questions that we need for the background knowledge around this one, and then we'll actually start reading the paper. So I'll just set up the context. And if you're new to the live streams, usually I just provide just enough context for you all to be able to understand the paper we're going through. Once you've done that, then we start reading the paper. So in this case, you don't have to go through I don't know how many papers you need to read before this. So let's take a look at all of these questions. The first one is, what is the stack dataset, which is the one this model is trained on? What is human eval in the context of this paper? This stands for most basic Python programs, I believe. It's another eval that the paper looks at. What are scaling laws? And what can we learn about how humans code? Cool. So the stack dataset is the plus Stack Overflow dataset. This is the first time, at least I have heard of it, and I was new to it as well. Looks like it has many examples that depend on files that are not a part of the dataset. It had a lot of files that just have boilerplate code. It's quite poorly documented, and the topics are skewed. So the takeaway from that is that many models are being trained on this, but it could obviously be cleaned up. So the authors of this paper actually do that, and that helps the training quite a bit. Evaluation for this paper. The first one is human eval. And the task here again for the model is to take a docstring, write Pythonic code, and it's being given a score of from 1 to 5 based on how well it does. The second eval is most basic Python programs. Again, exactly similar to above, and the task remains similar. So that is what the paper is being evaluated on. What are scaling laws? Very, very simply put, the more data you throw at a problem, the more compute you throw, the more emergent models become. So as you go bigger in size with these models, I don't know if you remember the meme of the circle and the small dot, right, between GPT-4 and 3, and that sort of went viral. It's exactly that. So as you as you go bigger in size, the scaling laws say that the models become more emergent or gain better abilities. But This paper asks a very fundamental question: if we can make the dataset cleaner, would that help these models perform better? I mean, a spoiler alert, of course it will. And that is also true to machine learning. So, this fundamental question sort of helps us end up with a 1 billion parameter model, which still is quite good for what it does. We also look at creating a simple data set. So we asked GPT 3.5, and the paper also sort of clarifies if you could have used GPT-4 in this case. I assume they were API credit limited or they were credit card limited. People usually say you're compute limited. I assume they were like GPT-4 was too expensive for this paper. But for the case of this paper, if you had used GPT-4, maybe you would have had better results even. So they use 3.5 model to create examples for the model to learn from, and they also use it to create simple exercises. Then they also use GPT-4 to clean up the dataset with annotations. So the point I had made earlier about all of these learnings from the stacked dataset, the authors sort of annotate bad examples using GPT-4, and we look at exactly how they do it, but I'm just setting up the context first. So they annotate the dataset using GPT-4. And then this is only done for a few examples. They use random forest with embeddings of the above to clean up the process. Sorry, to clean up the data set. So that is how they actually end up cleaning the data set in this case. So this is enough context for the paper. Now we'll actually start going through the entirety of the paper, and let me switch screen sharing. The chat is being quiet today. I hope my audio is going through. It's like always mildly terrifying when I don't see people making fun of me in the chat. How's everyone today? I don't know, guys. Please spam tea emojis to help my anxiety. I'm just worried if my video is going through and later on I realize it's not. Share my screen and let us jump to the paper. Cool. So again, the title of the paper is "Textbooks Are All You Need," and it's by Microsoft Research. There we go. I want a highlighter, please. There we go. It's by Microsoft Research, and I think this is a follow up. Hey, Rashmi, thanks for joining and thanks for confirming. Krishna, that is the coffee emoji, and if you mention that again in the chat, I will ban you from the chat. I'm just kidding. Cool. So, this is a follow up to the Tiny Stories paper. And when I was showing my tweet, I wanted to also highlight the summary there, but I've covered that already in another tweet. Tiny Stories sort of looks at creating very elementary examples of English based on which you can train a only English generating model. So it's a large language model that only does language modeling. I mean, I wouldn't know if you would call it a LLM or a LM given its size, but that sort of uses GPT-4 to create synthetic examples. That was also by Microsoft Research. I consider this to be like a follow-up paper or a part two of that paper. We also have Tariq in the chat. Thanks for joining, Tariq. Tariq is one of my smartest colleagues here at H2. I've worked quite closely with him during the last few weeks, and I blame him for not being able to live stream. We've been working quite a few weekends, and I completely blame him for not being able to live stream. Anyways, so as I mentioned earlier, this paper creates a model known as Phi 1. And everyone, please pay attention to this bit because it got confusing for me as well. They create multiple models. So Phi 1 small is the smallest model that they are able to create. I'm highlighting the bits I'm looking at. So please also pay attention to the yellow highlighter. So Phi 1 small is just a fun experiment where they say, okay, how small can we make this model? Turns out 350 million. Not that great of a model. Then they start training the actual model that they care about, which is Phi 1 base. Phi 1 base is the model before fine tuning stage. All right. After fine tuning, it becomes, as they call, the Phi 1 model. So Phi 1 and Phi 1 base are the same model. It's just different stages of fine tuning. All right. I was confused earlier. Are these different models? Why are they different on accuracy? It's just that reason. Cool. So it's a 1.3 billion parameter model, and it takes about 4 days on 8 A100s. Very reasonable given where we're headed in life. Uh, and they use GPT 3.5 for synthetic data creation, not GPT 4. That's an interesting insight from this paper. The fine tuning and all of this training happens on a data set of coding exercises. And they've sort of created these two evaluations where they report the numbers. Let me actually jump ahead. So, after all of this, the 5-1 model ranks third overall. Again, I'm highlighting what I'm talking over. So, you can see 5-1 ranks third, but it is one of the smallest models here. There's like one smaller model, which is CodeGen, but you can see that CodeGen performs much poorly. So these are the two evaluations, human eval and MBPP. We've already looked at these. The best one on these is GPT-4. So it scores 67% on one of them. It's unreported on the other one, but I would imagine it would still perform really well. Wizard Coder, which was very recent. So props to Microsoft Research for also benchmarking a fairly recent paper. That ranks second in human eval. Sorry, second in human eval, but it ranks worse on MVPP. I'm still putting it as second because I think I averaged these and it was still coming out higher. And then 5-1 ranks third. The cool thing for me was this rank was better than GPT 3.5. So if you look at GPT 3.5's number, it's 47% on human eval, and that's worse than the 5-1 model. Cool. Scrolling up a bit, they say that quality of data can drastically change the scaling laws. That's how they introduce the whole concept of this paper. And they say if they explore the improvement that can be obtained along a different axis, which is the quality of the data. They point out to the Tiny Stories paper, which I very briefly mentioned. And they say Tiny Stories also did something similar where they had a synthetic data set to teach English. And it showed that high quality data can actually really help with scaling laws. The human eval percentage between CodeGen 1 billion is quite a lot. I think you're talking about the difference, right, Shreyas? They're almost the same size. Yeah, I think he's talking about the difference. Cool. So it takes inspiration from the Tiny Stories paper. And they say, can we improve the SOTA of LLMs while drastically reducing the dataset size and training compute? So the task again is writing Python functions from doc strings. By the way, everyone, I'm curious. So this usually I used to write squiggle my notes while live streaming. This week I've written them already. Is this better for all of you that have been joining for a while? I'm just curious if this is a better experience. I assume it should be, but if you all prefer for me to like write down my terrible handwriting live, I'm okay to do that as well. As a YouTube uh, live streaming model, I appreciate any RLHF. Cool. So we've already gone through this, and just to point out Shreyas's fact, he was mentioning that 5-1 is. Let me change colors here. So let's pick red. 5-1 is 1.3 billion, and it scores about 50 and 55%. And then we have, I think he was talking about CodeGen, which is also 1 billion, but that scores quite poorly. One thing to point out here is it's just on these two evals. So I don't remember. I don't think if CodeGen extends beyond Python, but 5-1 only does Python, and that too only on very simple tasks. So I assume, of course, GPT-4 and 3.5 can work on many other things. I think Wizard Coder also does a lot of other things. So that's one thing to be mindful of, that this is not an exact judge of the entire coding capabilities of the model, but it's like it's a good insight on how small can we make it to be effective on this. Another thing that I forgot to highlight, if you all please will pay attention to the dataset size column, just glance through this and you'll realize this is the smallest dataset. So this really is the like win for this model here, which is that it's trained on the smallest data set size, and if you sort of normalize by that, this becomes the best performant in that case. So let's look at models that were performing better than this. We don't know about GPT-4, but let's look at Wizard Coder. Wizard Coder was trained on 1 trillion tokens compared to 7 billion. So if you look at that and you imagine how much compute would have gone into that, the 5-1 model sort of immediately becomes like a really cool model, right, compared to the other one. So that's the interesting thing here. So what they do here again is they pre-train on textbook quality data, both synthetically generated with 3.5 and filtered through web sources, and then they fine tune on textbook exercise like data. Let's scroll ahead and look at this graph. So I'm looking at this graph and I'm pointing out different things. I'm going from left to right. Remember, we looked at 3 different models, right? What were they? 5-1 small, 5-1 base, and 5-1. 5-1 small is a smaller model. 5-1 base is 5-1 model, but before the fine tuning. 5-1 small is a different model. 5-1 base and 5-1 are the same models. So this graph sort of looks at all of that, and we have 3 different data sets. So you have the original stack data set, you have code textbook, which is the cleaned up version of stack, plus the synthetic data set, and then you have code exercise. So the dark green represents the fine tuning stage, and the light green sort of signifies the pre training stage. The numbers being reported here are the human eval, and if you remember, we got to 51% for the best model. So the first and second graph are 5-1 small, right? And I think even for the smallest model, right, this is such an impressive number. So it's able to get to 41% still. And if you look at the biggest model, for all of these, you can see one insight, which is that this fine tuning stage sort of really helps. If you see the difference here, and same for the other 2 models, the accuracy sort of almost doubles, except for the 5-1 example where it sort of 1.6x is. I think this would be 1.6x, right? Something like that. My math skills are terrible than GPT-4, so don't at me. So the interesting insight again here is this fine tuning really helps. And if you look at what the code exercises data set is, it's just a bunch of questions. So it's just questionnaires where you're given dog strings and you have the answers, and it's just being fine tuned on that. So just that insight is also really cool to me, in the sense that even fine tuning on exercises, or as a human, I personally would like learn a lot just by practicing exercises, right? So as I was like I don't know, learning, when I was learning jacks recently, I would try to find exercises I wasn't able to, and I'd create them myself, try to solve them. I feel like this like questionnaire approach has personally helped me a lot, and I do this analogy while reading the paper. It apparently, as I understand from this paper, also helps these models quite a bit during their training stages. So here were the issues with the original stack data set. I've already pointed these out, but just to recap, it contains source code from repos with permissive licenses and web-based datasets. Here are the drawbacks. So it's a summary from these 4 points, but I've written it in the margins. Um, First of all, some of the examples have these like external imports. so they are sort of useless in that sense. A few of them have nothing meaningful, only boilerplate code. The good ones are sort of poorly documented, and the topics or use cases are skewed. See, the authors look at how to remove this noise and ambiguity, right? After they do that, they end up with a 6 billion token dataset, and then they create a synthetic dataset of less than 1 billion tokens. And another synthetic exercises dataset, which is very small. And this is also cool, right? Usually you read a lot while you're trying to learn a new topic. You like study a textbook and you answer these many questions, right? So again, that from human learning perspective is also replicated here. You train on 7 billion tokens, and then you sort of fine tune on 180 million questions. The key again is, as they point out here, fine tuning step is the key to unlocking emergent abilities. Cool. So how do they filter out this data set? Let's take a deeper look now. They begin with the publicly available Python code dataset, and they deduplicate this. So they annotate the quality of a small subset using GPT-4. The model is prompted to determine its educational value for a student whose goal is to learn coding concepts. Again, right? An example for how we learn. And after doing this for 100K examples, this is used to train a random forest classifier that uses output embedding from a pre-trained code gen model. And then it's sort of clean through that. Now, one thing I want to point out that was at least interesting to me was I'm looking at the code gen model here, and you can see that it's not as great as the other models. So I assume that they just use this model out of its smaller size. But I would imagine you can maybe improve on this, or maybe just this like simple step is also good enough. Maybe they could have been stricter with the cleaning up of the data set. But even with this, it gets to quite impressive results. I just assume if they just like used GPT-4 entirely, which would have been expensive, but just that to clean up the entire data set, maybe it could have done a better job. So here's an example of high educational value versus low. If you look at the right, it's just like variables being initialized, nothing useful here. And that is the end of the example. So again, these are not snapshots from the code, it's the entirety of the example that the model gets trained on. And on the left, you can see that it's sort of computing cosine distances, and it's fairly well documented, fairly well written code. Maybe even better than what I would write on my first pass. Cool. So the left one is a high educational value, right one gets discarded. And that is how we end up with a smaller data set. The second step is creation of the synthetic data set. So we have two synthetic data sets here, remember. The first one is similar to what we're training on. The second one is the exercises. So we're looking at the first one, which is more examples, simply put. Cool. So they also talk about here diversity in these examples is important, and it's quite useful for helping the model learn how to express and solve different problems, so on and so forth. So they talk about here the model needs to learn the right trick to be able to generate these models. Like how do we generate the right amount of diverse examples using GPT 3.5? So what they do is they look for ways to inject randomness into a prompt in a way that gives rise to generation of a diverse data set. This is obtained by providing constraints on topics and target audience of the generated textbook. I read this paper through and through 4 times before live streaming. I usually do that. I couldn't find more details around what constraints they had come up with or what topics they used. There's some in the appendix, I think, but not the exact details, I believe, around every single topic. So this is the secret that they're keeping to themselves, I believe. If anyone can check the appendix, I might have missed something there, maybe. But I believe this constraint on the topics is sort of the secret sauce that they haven't shared. Here's an example that they point out that's sort of synthetically generated, but apart from that, there's not a lot. Now, the second synthetic data set, or the third data set that we've been caring about, this is a synthetic exercises, right? And this was also generated by 3.5, where they looked at diversity by constraining the function names. They conduct explicit decontamination and evaluations to ensure that this is not causing a leakage in the evaluation. So they actually like have a very thorough section on it. I'm going to skip past that, but they actually really make sure that this synthetic data set is not causing any leakage whatsoever. So now here's some details around the model architecture. We've been looking at the 5-1 model, right? Again, going back to the evaluation, 1.3 billion model trained on 7 billion tokens. But what is this model? Let's take a look at that. I only scrolled up to point out 1B and 7B. Wow, so much scrolling. And we're here. Cool. So this is a decoder only transformer that uses flash attention, and I assume they use flash attention only out like instead of other tricks, because now flash attention is implemented in pytorch too. Hey, nothing wrong with doing that. I probably even couldn't do the right import. I'm not trying to make fun of the authors, but I'm just saying, maybe if you like also work on this approach and include the other recent tricks that help these models learn, maybe you could have even a more effective model. Maybe a 750 million model, who knows. And this still is quite approachable, right? So 8 A100s for 7 days of training is, I think, should be less than $1,000. So should be an interesting experiment for anyone working in research, I would imagine. I'm not a researcher, I'm just a paper reader. I don't know what that qualifies me to be. So the flash attention implementation is done for MHA, and then they follow the parallel configuration of attention layers and MLP layers similar to CodeGen, Palm, and GPT Neo X models. Here are some details around the number of layers and hidden dimensions. I don't think mentioning these out loud is quite helpful. Nothing quite stood out for me, but just these are some details around the architecture you can read through. Pause this video, read through it. I'm not going to. They also use a rotary position embedding, and then they share the dimensions of it. This was adopted from CodeGen model. I don't remember the citation. I just looked up. Literally, I looked up and found out it's CodeGen. I can't remember citations. They also use the same tokenizer as CodeGen small, I think, model. And finally, one more cool thing, they use DSpeed for training these models. So that's all the details we get here. After this, they also mention the batch size, the learning rate, so on and so forth. Nothing quite stood out for me here, so we're scrolling past. So in this example, they showcase the differences between these three models, right? And again, I'm not going to read through it, but if you pause and look at these, you can see that 5-1 sort of gets the answer perfectly right. 5-1 base doesn't. 5-1 small struggles as well. But this is proof that, hey, we're not just scaling up a model. This is the smallest size in their tests that they could come up with that gets the answer almost right. Then they also show that fine tuning improves the abilities to use external libraries. And the insight here is, even though the exercises did not contain the libraries that the model had to use, just because Pythonic implementations are so similar, or the Pythonic way is so similar across different APIs, it was able to pick up these insights of how to apply that knowledge, right? So they prove that point by actually testing it throughout this paper. So again, the insight is, even though it's not looked at some external libraries like Pygame and tkinter, it is able to apply these just by being fine tuned on the on the exercises data set. Now the cool thing again is it's just an exercise, right? It's just questionnaires, and even just that is able to teach the model all of this. Then they give an example of how to work with PyCode. And the only cool thing here was for me, I think somewhere they mentioned pew pew pew, which is which is how you which is the sound of shooting inside a game. But I'm just trying to look for it. Let me see if I can find that exact quote. Yep, here it is. So they say write a tkinter application with these details. If the text contains the word pew update, the text to pew 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 question mark. Otherwise no pew. So they give examples to prove the point that hey, 5-1 model actually is able to learn all of these skills and perform these emergent abilities. Cool. Then they look at evaluation with LLM grading, and there is an interesting point here, which is that how do you actually evaluate coding exercises, right? If like me, you don't like DSA, data structures and algorithms, you know that you have to pass a certain number of tests and then you actually clear the exam. That is not true for coding interviews, they claim in this paper, where you have a whiteboard which is very anxiety inducing and you have a human evaluator which is even more anxiety inducing, and you're trying to come up with O of n and you end up with O of n cube. But the point in the paper is these automated tests aren't effective. So what you actually need is a scale from 1 to 5 where you can get a grade. And of course, they use GPT-4 for this grading. So what they do is, first of all, they also create 50 new examples, problems, and this is created by humans that are unlikely to appear in the actual evals. And then they actually go ahead and also decontaminate, make sure that there's no leakage. But to evaluate, this paragraph basically makes the point that I just said. So this paragraph says that hey, coding evaluation is broken; it shouldn't be automated. So therefore, they decided to use GPT-4. And by using GPT-4, they're able to first of all use the LLM's knowledge, and then the prompt instructs the LLM to evaluate from grade 0 to 10, and that actually ends up with a score that we can see in this table above. So again, 5-1 performs the best against these examples. I'm sure if you would evaluate GPT-4 here, it would perform much better. But it just doesn't come up here. But still impressive results. Not to say that these aren't impressive results. Hey, One Pot Dish. I think One Pot Dish is a regular viewer. I've seen their name pop up every now and then. So in the section 5, they talk about how they actually remove leakage and clean up the dataset. So here they're not talking about the dataset for training. They're talking about evals and evals, however you want to say it. So they look at how to decontaminate those so that there's no leakage and you don't get a inaccurate estimate, like the MIT paper that was quite a discussion inside the community. But still, they look at n-gram overlap, and then they look at embedding and syntax based similarity analysis. So here they compute the L2 distance between the embeddings, and then they also create, I believe, here it is, ASTs to compare the code snippets, and based on that they deduplicate the dataset. This is quite nuanced, so I'm skipping over it. But after doing all of this, the model still sort of shines out. And the best part about it is it's still 10x smaller and trained on 100x smaller dataset size, but it still performs so well. So the point in conclusion that they make is we still can create many high quality data sets, and GPT-4 is of course really helpful for this. One challenge here is to ensure that you get all the diverse topics that you would want, and you want to make sure that it's non-repetitive. So this is something that the tiny stories paper I think did fairly well, and this paper at least doesn't share the details around it. Let's scroll past. So in the appendix, you can see different examples of how the model behaved and different examples for training. They talk about limitations as well, and they also talk about where the model fails, where it's bad. So it's bad at counting and spatial reasoning. They obviously point out that this model is not able to think of the bigger picture here, which you sort of need for programming, so on and so forth. Cool. So now before wrapping up and suggesting homework, which I usually do, I'll also show you all how to fine tune your own LLM if you'd like. So this will be using a completely open source tool created by the H2O team. And let me see if you all can see my homepage. Yes, you can. Let me visit LLM Studio. So this has been created by the H2AI Grandmaster team, and this is a no-code tool for you all to actually fine-tune your own LLMs. It's called H2 LLM Studio, fully open source. Everything's open source, no strings attached. You'll get this exact same thing, although it probably won't run on an A100 unless you have an A100 at home. Sorry, an A10G. So you can probably have something better than this. I think a 4090 is faster than this. I'm digressing. But this is the no code solution for fine tuning your own LLMs. It's fully open source. There's also a CLI if you want. So if you go to the GitHub page, you can also find a Kaggle notebook and a Colab notebook around how to make this work. So let me put this link in the chat real quick, highlight that, and then we'll get on with this tutorial. Inside here, you'll find all of the different details around how to install this. I've actually tested this and it really takes, I think, 10 or 11 minutes on Jarvis Labs and Lambda Labs. And locally, I think it's just like a bottleneck of your network. But all that to say, this isn't hard to install. Just follow these instructions and you'll end up with this exact interface. So, what does this interface do really? Here I can see the home page where I can see my finished experiment, my failed or stop experiment. I can see the name of the dataset and the examples. So if I hover over to settings, you can see that I can dump in my AWS key, I can dump in my Kaggle key, I can also dump in my Hugging Face key. So one cool thing about this interface is if I go to my completed experiments and click on a finished one, I can also push this to Hugging Face with all of the model card details. So just by clicking this, if I had put in my API key, this model would get auto uploaded to Hugging Face. And then you can share your fine-tuned model. So how do you end up with this? You first of all upload your data set, or you can import it through S3 or Kaggle. Here's a demo data set that I have, which is from Open Assistant. It just talks about very simple question and answers. So you can see it's just questions, instructions, and responses. And this also supports chats. So in the sense, you can see the parent ID column, which means this would be a part of a thread or a conversation where it would be coming from, right? I can also get the stats overview from here. I can get a visualization of the training data set. And after that, I can hover over to creating an experiment. So it's identified my data set, it's identified the problem type. After this, I can select the LLM backbone. So the H2 team really cares about making sure that all the models listed here are, I believe, good for commercial usage. So you can fine tune any of these backbones. What we'll do here is we'll take any of these models and then fine tune it further on this data set. So we've looked a lot during this paper on what it actually helps, how fine tuning helps, so on and so forth. This tool actually helps you get started with that fairly easily. So let's go with OPT 2.7 billion, and now you get all of the hyperparameters that you can possibly care about while training this model, right? So you have the special tokens, you have the separators, you can set the length of the prompt just through sliding around. You can also train on integer 8. Let's leave it at default right now. And I believe we're also looking at SPQR. So I don't know when, but at least for inferencing and also for training, we might have QLoRa implementation coming soon. Don't at me for that. After that, we can suggest select the optimizers just through this list, select the hyperparameters around that. And we'll, of course, do LoRa fine tuning. I assume everyone is familiar with that, and we can set the parameters for it. I'll change the metric to blue, but if you want to use GPT 3.5 or 4 for evaluation, you can also do that. And once you've done that, I can hit run experiment. It'll start training this, fine tuning this model, and we'll get LLM at the end of it. While it's training, you'll get this single page overview where you can see how it's doing on validation examples. So you can see the best examples, you can see the worst examples. I started reading through this, but let's not get distracted. And this is one of my favorite features, which is you can also chat with this model. So right now the GPU is blocked by another experiment, but you can also chat and get a feel for these models as they're being trained. So again, this is completely open source. Check it out if you'd like, and I would invite everyone to play with this to fine tune your own models. Here's the link once again. And to wrap up today's live stream, let me suggest some homework like always. Write about this paper. I've learned a lot more throughout my career by sharing knowledge and writing about it on the internet. I've learned even more through live streaming. I don't suggest it to anyone. It's a very boring activity. But consider writing about this since you spent time watching this video. Share about this paper with the world. It also sends a signal that hey, you've learned about this paper. Read the Tiny Stories paper, or at least my summary of it. So let me head back to my Twitter and point this thread out. There we go. Not this tweet. If I scroll down, here's my summary of Tiny Stories. You can read through this if you'd like, or you can read through the entire paper. This was one of my recent tweets. So just in the thread of this paper summary, you can find a link to Tiny Stories. So if you want, read through the Tiny Stories paper and consider checking out LLM Studio or H2GPT. H2GPT is an open source LLM that the Grandmaster team has created here at H2. So I also invite you to check that out. It's at this particular link. Let me share that as well. You can see that this is a familiar interface, and I'd suggest that you can also play around with this. This is also fully open source, good for commercial usage. These are different models that are based on different backbones. We have models based on the Falcon backbone and Open Assistant backbone as well. This one is Falcon 40 billion. There's a lot of those. Check these out if it's interesting to you. You can also enable this functionality, which we're quite proud of. So you can search the web and play around with it. This is being hosted somewhere, of course, but if you head to this link, you can find the exact details around the model, and you can download it and run it on your GPU as well if you want. So let me catch up with the chart. And one pot dish has a question. Um, I don't think this is specific to the LLM Studio thing, right? I mean, it is possible, but I don't think this is relevant to LLM Studio. Yes, it is possible. Thanks for joining, Karthi. I think I will try to live stream every Saturday, although I've been traveling quite a bit fairly recently, so it might not happen. But at least I'll try to live stream once every week about some LLM paper that I really enjoyed from that week. So cool. That's it, everyone, for this live stream. Thanks for joining. We'll keep meeting every week, hopefully on the exact same time on Saturdays. And the LLM roadmap is coming soon. I've been working on it. I sort of teased it as well. Let me know if you enjoyed this paper, and let me know if you have any suggestions for what papers you all would like me to cover next. Apart from that, I've been covering papers every single day on Twitter and also on LinkedIn. So you can check that out as well. I've decided to share one paper every day because I have no life. But thanks for joining if you did.